Well, good morning. It's 11:42. We're 12 minutes late getting started. I had students in my office from the last class until now, nonstop, and it's just been crazy. But still, there's no one in the classroom but me, so I guess we'll pick up from where we left off last time. And what my memory is, and I'm pretty sure I wish someone were here to remind me. I'm pretty sure we did Theorem 4.4. But that's where I have one mark. But I can't remember that we did sets that are not vector spaces. Or maybe we did. Yeah, I think we did do that. So I think we are at the beginning of 4.3. In fact, I guess we had started 4.3. Though I don't remember it. Maybe I just didn't notice my mark there. Okay. So I believe we're starting at 4.3. No one's here to contradict me, so that's where we'll be beginning. I do have some announcements, some pretty important announcements, but I sort of want to wait till somebody gets in the class to make the announcements. So anyway, let's just pick up and go from here. Chapter 4 is vector spaces. 4.3 is subspaces of vector spaces. Now, first, in many applications in linear algebra, vector spaces occur as subspaces of larger spaces. Okay? Now, lots of space there. You have vector spaces, you have larger vector spaces, and you have subspaces of the vector spaces, and those can be those are vector spaces themselves. For instance, you'll see that the solution set of a homogeneous system of linear equations in variables is a subset of R sub n. Okay? So, sorry. All right. That was sort of a, find that the solution set of a homogeneous or homogeneous system of linear equations in n variables is a subset of R sub n. So remember what R, I see saying sub n, is R superscript n, Rn is how I like to say it. Rn, that's n space, that means n-dimensional space. And if you had a homogeneous system of linear equations, okay, think matrix here, okay, with n variables, then the solution set has to be a subspace of Rn. Certainly all the elements in Rn are not going to be solutions, but all the solutions have to be in Rn, so therefore it's a subspace, okay? A non-empty subset of a vector space is a subspace when it is a vector space with the same operation defined as the original vector spaces, as stated in the next definition. So here's the definition of a subspace of a vector space, okay? Get my pen set up. Okay. A non-empty, okay, now the symbol for that, well, let's just leave it like a non-empty subset W of a vector space V okay, so vector V is a vector space, okay? It meets all those 10 criteria, okay? The addition criteria, the multiplication criteria, yeah, all those criteria that we talked about before. That's a vector space. This non-empty subset W of a vector space. Now when they say subset, that's different from being a subspace. It's a subset, meaning every element in W is also in V, vector space V. Now certainly it doesn't mean that all elements in V are in W. It could be, but generally that's not the case, okay? A subset is all the elements in W are elements in your vector space V, okay? But it is a subspace, W is, when W is a vector space itself. Okay? Under the operations of vector addition, they just say of addition now, just to keep you from confusing it with vector addition. We call it vector space, but remember they don't have to be vectors, okay? The operation of addition and scalar multiplication. Okay? Multiplication. Something like that. Pretty ugly writing. Defined in V. Okay. Now, several little but not necessarily minor things going on. Number one, this subset W has to be non-empty. Certainly an empty set is a subset of every space in every set, okay? But we want this to be a non-empty set, okay? It has to have elements in it. And saying it's a subset of a vector space, meaning that all its elements are in the vector space. But that's all a subset means. Vector space means, of course, it has meet all those 10 criteria, okay? But this subset W is itself a vector space, is a vector space when W is also a vector space. So a subset W of a vector space V will be a subspace of V if W itself is a vector space. You can have subsets that aren't vector spaces, but it's a subspace when W is a subset and also its own vector space. And it has to be under the same operations of addition and scalar multiplication that were defined originally for V. Okay. So here's an example. Example 1, a subspace of R3. Okay? I'm going to start anew just in case I need more room. Show that this set W defined to be x1, 0, x3. Okay? Such that, now that's a set. Okay, wait, it's a set of ordered triplets. Okay? Set of ordered triplets. Wait, sorry. Put the set notation too soon. Set of ordered triplets x1, 0, x3, such that x1, x of 1, and x sub 3 are real numbers Okay, that's all. Such that there are real numbers. Okay? Show that that is a subspace of R3. R superscript 3. With the standard operations. With standard operations. Okay. Now, okay, just a little bit of a thing here. R3 would be the set of all ordered triplets, x1, x2, x3, where x1, x2, and x3 are all real numbers. Okay. So this is the set of all ordered triplets. The same x1 and x3, but now your x2s are all 0. Okay? So in other words, this is the xz plane. Okay? I wish somewhere in the room I'd pointed out to you what we mean by that. R3 would be all of 3 space. All spaces we understand it. X, Y, and Z. Every ordered triplet in that. Okay? This subset W of x1, 0, x3 means you're in the plane, the xz plane here, but nowhere other than the plane. You're not in any space to the right of the plane or left of the plane, you know, just in that plane. Well, certainly, okay, well, without doing any more. Now, what are our standard operations? That you add 2 vectors together and you get a vector, okay? And certainly you add any 2 vectors here together in that plane, you're going to get another vector in the plane because the y cannot go out of the plane. The x's, 1 and x3 are any real numbers, positive, negative, fraction, decimal, rational, irrational. It doesn't matter. So as long as you're there, you're in the plane, and those vectors will be in the plane. Any 2 sum of those, your middle one will always come out being 0, and the other 2's will be real numbers. Okay? That's your standard operation of vector addition. Standard operation of scalar multiplication. Multiply any scalar, C, times any of those vectors there, and you get C1, x1, or Cx1, 0, because C times 0 is 0, and C x3. Well, those are real numbers as well, and they are in, so that's also in that plane, in the xz plane. Okay? Now, you have to confirm that all your other elements are met, and those are pretty easy to meet. If you go back to page 155, we've already said that the sum of 2 vectors is in that space W, so that fits. Doesn't matter which order you add them, the commutative property fits, associative property fits. The 0 vector is in there because x1 could be 0 and x3 is 0. x2 is always 0, so the 0 vector is included, so you're fine. And for every u in v, there's a vector negative u, which would be negative x1, 0, negative x3, which is in the space, and it operates as it's supposed to. Scalar multiplication, Cu is in this, we already mentioned that one. C times the sum of any 2 vectors in that is C times the first times C times the second. Yeah, you add 2 vectors, U11, 0, x11, 0, x31 plus x12, comma 0, comma x32. Add those together, or multiply those, each of those by, everything works. Okay, the commutative, the distributive, all those work. Okay, so therefore W not only is a subset of V of R3, it is also a subspace of R3 because all the rules met. Certainly it's non-empty, that's required. And as I said, it's the XE plane, and being the XE plane, that's closed under standard addition. Any sum of two vectors in the XE plane also lies in the XE plane. And the sum adds, okay. All of them fit, okay? To establish that a set W is a vector space, you must verify all 10 vector space axioms. That's what we just sort of talked through quickly. If W is non-empty subset of a larger vector space V, and the operation defined on W are the same as those on V, however, then most of the 10 properties are inherited from the larger space and need no verification. The next theorem states that it is sufficient to test for closure in order to establish non-empty subset of a vector space is a subspace. So here is the test, okay? I think we talked through the others, so it's okay. Here's theorem 4.5. If W is a non-empty subset of a, starts a lot like the other, of a vector space, VS is vector space, V, capital V, then W is a subspace of V if and only if the following closure conditions hold. So these, from now on, are all you really have to prove. 1. If U and V, I'm writing them as if they're vectors, but they're whatever the elements are in W, then U plus V is also in W. That's required. Secondly, if U is in W and C is any scalar, then CU is in W. Okay. So, if those two closure conditions hold, that's all you have to do to show it's a subspace. Now, they say it's true, but it seems like to me you still have to go back and verify that you contain a zero vector, because that is not covered by any of these. So I sort of want to say that doesn't seem like quite enough, okay? Close to being enough. Okay, yeah, it is. Because if C was any scalar, that could include the zero. And if CU then would be the zero vector, it would have no choice but being the zero vector. And if it's in W, then that would guarantee that the zero vector was there, I guess. Okay. Because the subspace of a vector space is also a vector space, it must contain the zero vector. That's what I was just worrying about. In fact, the simplest subspace of a vector space V is one consisting of only the zero vector. So if W, the subspace of any old vector space, happens to be just this element, the zero vector, okay, then this is called the zero subspace. Okay, now if you think about it, if U and V are both in W, well, they have to be both zero vectors. You add them together, that's a zero vector, and that's in W. So the first condition's met. And if U is, oh, thank you. All right. I'm tired of talking to myself. Okay. I left my paper at a certain place, and I couldn't remember for sure if that's where we ended or if I just happened to put the paper in the wrong place. And I had a mark on that page, but I didn't think we got that far, so I hope I started at the right place. Let me get the projector turned on and the light turned on. We'll get back to it. Okay. I didn't make any announcements at the beginning because no one was here. So let me go on and make it. These are both leftovers from before. There's a company named No Kid Hungry working to end child hunger in America today by ensuring all children get the healthy food they need every day to thrive. The job title that's open is Brand Ambassador, which I don't know exactly what it means. I guess you're ambassador for this company name, No Kid Hungry. Job description, I think I read those to you last time, didn't I? Okay. Send out items through the mail to the list of orphanage homes that would be provided to you in your city. Okay, so evidently they're sending food items out to places that need them. And you're also mailing out letters of invitation from this company to other non-governmental organizations, foundations, or businesses in your city. It sounds like you're fundraising, okay, support raising. Okay, interested candidates should contact Henry, which is sort of strange to say Henry, via email, and the email is HS and then looks like 7 digits @gmail.com. So I assume H is for Henry, S is for the last name, but it never gives the last name. And then I don't know what the 7 digits stand for, but anyway, they are @gmail.com. Weekly wages are $350 a week, and they're looking forward to hearing from you. Now, this was sent by Coach Henderson, who is Jonathan Jefferson. Coach Jefferson, Jonathan Jefferson, who I assume is a coach here at Lawson State. I don't know what he coaches, but it says he is. So that's all I know about it. If you're interested, the information's up here. Okay. All right. The second one is one of the summer research experiences for undergraduates. They're called REUs, Research Experience for Undergraduates. This one's out of UAB, and the dates for this REU program will be May 17th to July the 24th. And the title of it is Experimental and Computational Materials Research. Okay? The research projects include, but are not limited to, electronic materials, nanomaterials, laser and optical materials, biosensors, biophysics, and biomaterials, and computer modeling. So any undergraduate student with diverse backgrounds in physics, chemistry, applied mathematics, and engineering could apply. Okay? The scientific research projects are developed specifically for undergraduates by an interdisciplinary team consisting of science and engineering faculty at UAB. There is a recruitment poster. Oh, I had them put it on the board in the hallway near the career services. I was going to put it here, but because it's at a high traffic area, this isn't that high traffic, so I had them put it down there. I remember now. Application deadline is March 15, 2020, so it's quite a ways off, but good idea to get started now. Decisions will be made no later than April 15th. And we got some more information here, websites, emails, all sorts of things. If you're interested in that one, it's here too. Okay. Now that's outside the college. Within the college, I've been asking for weeks, are we doing student course evaluations for this fall? Nothing that I saw was published anywhere until yesterday. And so now they're open and you can go out there and do your course evaluations. Please do. What's that? I think you can access them through Blackboard. The easiest way probably is check your email, and in your email you'll probably have a message about them. There'll be a link there. You can click on the link and you're right there. But you could probably get through it through Blackboard. I know you can get through it through the Boston State webpage, but the easiest way is through that email. Do you get Boston email?
I have Boston email address, but I rarely get on it.
You're right.
I rarely get on my
Right.
email.
Well,
Boston, but I know how to access it.
right. Okay. Well, if you access it, I know you'll find the email there. If you left both any other email address, they may have sent it to that one as well. I don't know if they did or not. I don't know how many they sent to. They may have only sent to official Austin. I don't know. So check that, and please do the student course evaluation. They don't really take that long, and they're really valuable to us. Okay. So please do those. All right. Now, okay, that's school line. Now let's get down to the course announcements. There is a research paper due in the course, remember? Okay, so don't forget that. I've only got 1 out of 3 in.
I actually emailed it.
Oh, you emailed it to me?
Yeah, before I came into it.
And what?
Before I came into it, I emailed it like around, it was like 10 o'clock.
Today?
Yeah.
Okay, I haven't been on email today yet. Okay, so I'll try to get on it and get it printed. Okay? You and one other student have turned in test 1. The third student hasn't. You and that one other student have turned in test 2. The third student hasn't. The other student has turned in test 3. I don't think I got your test 3 yet. Okay, good. So I need those in by Thursday. Okay? And your research paper by Thursday. Oh, you've already sent it. Okay? And I will be giving you the last test on Thursday after class, as far as we get in chapter 4. Okay. Now, when is it due? Anytime after Thursday. If you get it to me later Thursday or Friday, okay, let me tell you about this Friday. I've got a doctor's appointment at 9:20. So that means I'll be on the Birmingham campus at 8, but I have to leave there by 8:40, say, to get to my doctor's appointment at 9:20. So I'll only be there 40 minutes, okay? Then the doctor's appointment is 9:20, and I don't know how long it's going to take. It's my annual physical, and he canceled on the last one. He did, not me. So I haven't seen him for a year and a half. And so I don't know how much he needs to do. I don't know if he's going to need blood work, lab work. I don't know what all is going to be included in it. So it could be a very short visit. It could be he's running late. They always do. It could be that it's going to take a while. If I get out of there in time to get back to campus before noon, I'll go back to campus before noon. However, if I don't, I'll be going home after that. So I can't say when I'll get back to campus or if I'll get back to campus. So if you're going to do something on Friday of this week, for sure, there's only 40 minutes, okay, 8 to 8:40 approximately. There may be time after that, but I just won't know until we get there. Okay. So, when else would the paper be due? Anytime the following week, okay? And let me just give you my office hour, where I'll be when, okay? On Monday of that finals week, I'll be here on this campus in my office, 265, from 8 in the morning until 6 in the evening, all day long. Have other classes that day, but they're all doing take-homes and bringing them back to me. Okay, Tuesday, I've got a final exam down at 205 from 8 to 10, okay? It may go a little over 10. It shouldn't, but it may. So I'll be there somewhere around there until close to 10 o'clock, around 10 o'clock. Okay, then I'll be going back to my office then. So if you bring something in 8 to 10 on Tuesday, you can either slide it under my office door or bring it to me in 205. Okay. After 10 o'clock, I'll be in my office until about 3:15. Because at 3:15, I've got my second mini-term class. Because it's a mini-term, we actually have class that first day of finals. First day that they would be meeting on Tuesday. So I'll be in class probably no longer than 4:15, 4:30, if that long. And that class meets in this room. So you can either catch me here between 3:15 and 4 or 4:30 or something like that. I'll be here. If I'm not here, I'll be down in my office. I'll be here until 8 o'clock at night, okay, in my office. Then on Wednesday, on campus, this campus from 8 until 4. At 4 o'clock, I have to leave to go to the Birmingham West campus to collect finals there. So I'll be there from 4 to 6:30. Okay. Well, 4:30 to 6:30 because it takes me about a half hour to get there. So between 4 and 4:30, I'll be driving over there. Okay. That's Wednesday. Thursday, I'm back here on this campus, and I'll be here from 8 o'clock in the morning until 3 o'clock in the afternoon. 3 o'clock in the afternoon, I'll be in this room giving a final exam. That will not take long, okay? Let me back up. I said the Tuesday will be 3:15. I said till 4 o'clock. Probably make that 4:30 or 5 because what we got to do, I've got to pass out all the old materials, the labs and the tests. We're going to be doing a lab and taking a test. So let's say I'll be in there for probably 3 hours. Okay. So from 3:15 till 6:15. But other than that, I'll be down in my office until 8. So on Thursday, though, all that I'm doing is giving a final. And it's not going to be very long. It'll probably start around 3, and they'll probably be through before 3:30 or 4. So after that, I'll be down in my office until 8. Okay, Friday, that's next Friday, not this Friday. Next Friday, I'll be on the Birmingham campus, 8 to 12. Okay. Oh, well, let me think. I think graduation is that Friday. So I'll be on Birmingham campus, so I won't be available the whole time because we'll be at graduation. I don't remember what time graduation is. Maybe in the afternoon. So 8 to 12 may still be safe. I don't know. I can't recall. Okay. Then, grades are due by, I think, noon on the next Monday. So I've got to have everything in next week, okay? But I will be on campus from 8 till probably 4 on Monday, Tuesday, and probably Wednesday. I don't think I have to stay late those days. So I'll be here at least 8 to 4 those days. But grades are due in by noon on Monday. So if you don't have things in, it's going to be an incomplete, but you can bring them to me. And then I'll change the incomplete to a letter grade. Okay. All right. Now, what we're talking about here, we're in Chapter 4, Vector Spaces, 4.3, Subspaces of Vector Spaces. We'd already done the definition of a subspace. And let me just review it quickly. Let's say we have a vector space. Vector spaces have to meet all 10 of those criteria, remember? Okay. Half of them deal with vector additions, half of them deal with scalar multiplication. Now, when I say vector here, remember vector can be anything. Matrices, equations, polynomials, functions, not equations, functions, just a whole slew of things, okay? But we call them vectors. So, if you have a subset of a vector space, and usually they call it subset of W. If it's a subset of a vector space, okay, here is one. Ordered triplet x1, 0, x3, okay, where x1 and x3 are any real number in the world. That's a subset of R3, because R3 is a set of all ordered triplets, everywhere, okay? But this one, the Y one, is 0. So if that's X, this is Y, and this is Z, that's the XY plane, okay? So this is a subset of all of space, right? The XY plane is a subset of all space, okay? Now, is that also a vector space? Well, a vector subspace of R3. It is, because it also meets all those standard operations. It itself is a vector space. That plane is a vector space. Any two vectors in the plane add to be a vector. Any scalar, real number, multiplies to be a vector in that plane. Okay? So, here was on page 162, near the bottom of the page, a theorem that said, rather than going through all 10, you could just do these two. If W is a non-empty subset of some vector space V, VS stands for vector space, then W is a subspace of V if these two criteria are met. Okay? The first, that if any two vectors, and I'll list them as if they're vectors, remember they could be matrices, functions, polynomial, they could be anything, almost, I guess you would say. But if these two elements of W, okay, if these are elements in W, then the sum of these two is also in W, okay? So, that almost looks like the closure principle, which was like number 1 and number 2. But if that's met, and if U is an element of W, and C is any scalar that you happen to choose, then CU is also in W. If that condition is also met, then, if these two conditions met, then W is a subspace, not just a subset, but a subspace itself. It is a vector space if these two conditions are met. And I hesitated a little bit because I said, where is the guarantee there'll be a zero vector there? Okay? Well, if this is met and U happen to be the opposite of V, then U plus V would be the zero vector, and this implies that that is also V, so the zero vector is there, and if U is a element of W, and C is any scalar, including the number 0, 0 times U would be the zero vector, and it says that's also in W. If those are met, then you're guaranteed to have the zero thing. Now, the next thing we did, and this is the top of page 163, the simplest subspace in existence is W contains one element, the set that contains the zero vector. Okay? Now, and we call that the zero subspace. It's not empty, but it has a zero vector in it. An empty subset would be no elements in it. This has one and only one element. Does this meet the criteria? Well, if U is in this, which means U would be the zero vector, and V is in this, that means V is a zero vector. U plus V would be in this because they add to be the zero vector, and it would be in here. And if U is in here, which means it's a zero vector, and C is any scalar in the world, C times the zero vector is a zero vector. That's in W. So, yeah, that is the simplest subspace in existence, the zero subspace. It contains only one element, and that's the zero element for whatever that was. Okay. Now, another subspace of V is V itself. Okay? Remember, V is a vector space, and the subspace, a subset of V would be V. Okay? That's every element in V is in V, so that's a subset. And because V is a subspace, then of course V is a subspace. So it seems redundant. Every vector space contains these two trivial subspaces. Such spaces other than these are proper or non-trivial subspaces. Okay? So the zero subspace is a trivial subspace, and the subspace itself is a trivial subspace. Any other subspace that is not either zero vector or the entire subspace is called a proper or non-trivial subspace. Duh. Okay. Some of these definitions, you think, why do you need these? But you really do. Here's example 2. Let W be the set of all 2x2 symmetric matrices. I can't write. Symmetric matrices. Okay. Whoops. Show that W is a subspace of I don't have a symbol for subspace. I'm going to call it SS. That's subspace of the vector space, VS, and this vector space is M22. That's the set of all matrices, 2x2 matrices. They don't have to be symmetric matrices. They just have to be matrices with standard operations of matrix addition and scalar multiplication. Okay. Now, I was going to point you back, but I'll tell you, they say it here now. A square matrix is symmetric when it is equal to its own transpose. It's a square matrix is symmetric when it is equal its own transpose. Okay. Now, M22 is a vector space. Okay. That's the set of all 2x2 matrices. All 2x2 matrices. So certainly, this is a subset of that. W is a set of all 2 by 2 matrices that are symmetric matrices. Okay? Now, remember, we only have to meet 2 tests. The closure under vector addition and scalar multiplication. Okay? Those are the only 2 we have to make. So therefore, if we have, okay, well, one other thing. You have to say W is non-empty. Well, we've just said W is a set of all 2 by 2 symmetric matrices. Well, there are 2 by 2 symmetric matrices, so therefore it's a non-empty set. So you sort of have to say that one, get that one done up front. Okay? Then you have to show that these 2 operations happen. Okay? Now, what if you have 2 matrices? Goodness gracious, the pen's doing really strange. A1 and A2. Now, why they choose A, I don't know. These are 2 by 2 symmetric matrices, A1 and A2. Okay? Now, because they are symmetric, that means A1 is equal to A1 transpose, and A2 is equal to A2 transpose. That's the definition of a symmetric matrix. It's equal to its own transpose. Okay? Now, what we have to show is that A1 plus A2, that first condition, the scalar multiplication, that its transpose is indeed a symmetric matrix. Okay. Now, I don't know if you recall, and I should have looked this up beforehand, but I had people in my office nonstop in between classes. I mean, literally nonstop. It was just amazing. I think it's back on page 57. Okay? Back on 57, I believe. Let me check that out. Yeah. And here are some properties on page 57 of the properties of transposes. Okay? First, if you look at number 2 from page 57, you see that this quantity here, A1 plus A2 transpose, is equal to A transpose plus B. I'm sorry, A1 transpose plus A2 transpose. Okay. Now, what was required? What was required that A1 plus A2 the sum of those must be in W. Okay? Well, sorry. Is the transpose of this equal to itself? Okay? Because A1 is equal to A1 transpose and A2 is equal to A2 transpose, this means that this is A1 plus A2. Okay? And we've just said the A1 plus A2 this is, the sum must be, okay, we've got to show this as a symmetric matrix, okay? And we've just shown that the transpose is equal to itself, okay? So therefore, it is closed under addition, matrix addition. The second is under scalar multiplication. For any C times A1, okay, on the page here, I think. Somehow I got off. Yeah, here we go. Okay. C times A1, we know that has to be in this because it's a well, if we take this and do the transpose of it, okay, then you get, and this is from number 3 on page 57, that this is the same as C times A transpose, okay? Well, C, A1 transpose, okay? And C times A1 transpose, because A1 transpose is A1, this is the same as C A1, okay? Well, scalar multiple is also closed under there because CA1 transpose is the same as CA1. So we've shown that both of those have to be true. If A and B are symmetric matrices of order 2, so is A1 plus A2, okay? Similarly, W is closed under scalar multiplication because A1 is equal to A is equal to A transpose, CA transpose is equal to CA transpose, which is CA, and if A is a symmetric matrix of order 2, then so is CA, okay? Now, here's a generalization of this. For any positive integer n, the set of symmetric matrices of order n is a subspace of the vector space M in N with standard operations. Okay? So the next example describes a subset of M in N that is not a subspace. Okay? So let's go to this one. We're going to let W be the set of singular matrices okay, of order 2, okay, set of singular matrices of order 2. Show that W is not a subspace of M22. Subspace of M22, which is a set of all 2 by 2 matrices. Okay? Okay. Now, do you need a little refresher on what we mean by singular? Okay, singular means it's what? Okay, that it does not have an inverse. Right. Singular, non-singular, invertible, non-invertible, they are backwards from each other. Okay. If it's invertible, it is non-singular. If it's non-invertible, it is singular. Okay. So yeah. So it does not have an inverse. Okay. So it says that B be a set of singular matrices of order 2. Show that W is not a subspace M of M22 with standard operations. Okay. Now, to show that something is not, all you really have to do is come up with one example that would not be true. It's sort of hard to show that all examples aren't true because some may be, but you just have to come up with at least one that isn't. Now, if W winds up being empty, it's not a subspace. Well, obviously W is not empty because it's a set of all singular matrices. Okay? So that one's sort of out. Now, is W not closed under addition? Okay? Or is W not closed under scalar multiplication? Those are the other two. It can't be empty, and it has to be closed both under addition and scalar multiplication. Now, let's take a matrix A that is singular. And they just pick one, which is 1, 0, 0, 1. I mean 0, 0. Okay. Now, why is that not singular? You cannot get that to become the identity matrix. No matter what you do to it, there's just no way it can happen. So that's a singular matrix. Okay. Now, let's say B is also a singular matrix. This time they put the row of zeros at the top and that at the bottom. Okay. Now, what happens if you add those two together? And that is a singular matrix. So there you've got it. That these two non-singular matrices, you add them together and you don't have a singular matrix because the identity matrix is a singular matrix, is a non-singular matrix, and for it to be closed under addition, any two that you add together must form a singular matrix, and this does not. It forms a non-singular matrix. Okay? And singular means non-invertible, non-singular means invertible. The identity matrix is invertible. This is not. So W is not closed under addition. And by the theorem, which said if and only if, okay, it's not a subspace of M2 because it's not a vector space itself. Now, they came up with that one. There are probably plenty of others you could come up with. That's probably the simplest because those are obviously singular, but when you add them together, you get the identity matrix, which is very obviously non-singular. Okay. So, example 4. Show that W, which is a set of all ordered pairs, x1, x2, such that x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Okay? With standard operations, is not a subspace of R2. I wrote too much of the word. Okay. Now, it's obviously a non-empty set, okay, because it has elements in it, okay? 7, 3 are in it. 7 is greater than 0, 3 is greater than 0, so it's not empty, okay? So that one's okay. Your addition is going to be fine, okay? Because add any two vectors together, you're going to have a vector whose first and second component are greater than or equal to 0. So it's closed under addition. Okay. Scalar multiplication, though, I think is where we're going to find our issue. Because let's say we have x1, x2, okay, where x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Let's multiply that, remember, by any real number c. So let's multiply that by minus 1. That's a real number c, right? Well, what do you get now? This is minus x1 minus x2. But now these are not greater than or equal to 0. These are less than or equal to 0. And therefore, okay, I wanted to add this. x1 and x2, let's take them both being greater than 0. They certainly are going to be in that set. And if they're both greater than 0, then those are both less than 0, so that's not closed under scalar multiplication. Because obviously that's not in W. So that's not a vector space. Now, yeah, and that's exactly what they did. They didn't use the generic form. They used a specific number, 1, 1, which is fine. You could use any two you want to. Multiply that by minus 1, which is allowed, and you get minus 1, which is not an element of W. So it's not a subspace. Okay. You will often encounter sequences of nested subspaces. For instance, consider the vector spaces P0, P1, P2, P3, up to Pn. For P sub k, I guess I should be writing this down. Oh, you got your book, right? Yeah. Where P sub k is a set of all polynomials of degree less than or equal to k. So P0 would obviously be all monomials, okay? There's none less than that, you know, degree less than or equal to k. We're not counting degrees ever being negative. So P0 would just be all monomials. P1, I'm sorry, not just monomials, all real numbers, basically, okay? Let's see if that's true. Yeah. Okay. P1 would be all polynomials of degree less than or equal to 1. So those would be all linear and constant polynomials. Okay. P2 would be all polynomials of degree less than or equal to 2. So it would be all quadratic polynomials, linear polynomials, and constant polynomials, and on and on and on. Okay. Now, and they all have the standard operations. You can now say that P0 is a subset of P1 because, I guess I have to write some of this down. I was trying to avoid that. Let's go and start from, just in case this takes longer than I thought it would. Okay. Here we have vector spaces, P0, P1, P2, P3, dot, 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 all the way up to including Pn. Okay. Where P sub k is a set of all polynomials of degree less than or equal to k. Okay. So, with standard operations. Okay. Of polynomial addition and scalar multiplication of polynomials. Okay. Now, like we said, P0 would just be all numbers. Okay. All, sorry. Sorry. Goodness gracious. All numbers. I mean, it's just polynomials of degree 0 are constants. All constants. Okay? Positive, negative fractions, that's whatever. P1 are all first degree and 0 degree polynomials. So certainly P0, all P is a subset in a subspace of P1. And then P1 and P0 are subspaces of P2, and they're nested like that. That's what they mean. So then P0 is a subset of P1, is a subset of P2, it's a subset of P3, it's a subset of P4. Oops. I don't know what my pen's doing. Okay. And we'll dot, dot, dot this. And I guess they put a subset here. All the way up to and including P sub n. Okay. They don't go infinitely. They some fixed value. So one way of saying that, if they use J and K, yeah, if J is less than or equal to K, then P sub J is a subset of P sub K. Okay. Only they're saying subspaces. So I don't know if this symbol represents subspaces as well. I think these just represent set. So I'm going to put is a subspace of P sub k. Okay. I won't use that symbol because I think that only means subset. Okay. It's actually subspace. Okay. And example 5 is going to be another nester. Okay. So let's see that. How are we doing on time? Oh, I don't even have my watch out. Do I? Oh man, did I leave my watch either in the last classroom or in... No, there it is. I put it in the wrong pocket. What do we go to? 11. time already? Okay, let me think. I get so crossed up on my time. We started late. We went from 11:30 to 12:45, and it's past 12:45, isn't it? Sorry about that. Okay, no extra charge though. All right, we'll pick up next time at example 5. Okay, sorry about that. All right, the homework exercises here would include, we made good progress in 4.3. Any of the odds 1 through 5. I'd say 1 or 3 and then try 5. Any of the odds 7 through I'd say 7 through 13, and then try some of the odds 15 through 19. Okay? Some of the odds, any of the odds 21 to 23. And by the way, all these odds are at calcchat.com. Okay? Any of the odds 29 to 35. Any of the odds 37 to 41. And I think maybe we can stop there. We'll pick up the rest of them when we finish the rest of the section. Okay, sorry about that. All right, and again, we'll go as far as we can in chapter 4. Now, I warn you this also. I've got to make up the test before we meet, so therefore I'm probably going to overshoot. So some of the questions on there will be outside, and they'll be bonus or optional, whatever you want to call them, and the others will be required. Okay, so I'll just let you know that because I can't predict well enough how much we're going to go. Okay, so good deal. And the other two never showed. I'm sorry, I can't hear.
Test 3.
Test 3?
Yeah.
Okay, all right. That'll be fine.
Yes, sir. All right. I'll see you Thursday.
Okay, thank you.